calculating physical quantity using this technique. First is most simplest quantity is hadron mass. Since the proton and neutron are made of quarks, their mass itself is not so easy. It's not sum of the mass of the three quarks. Almost all hadron mass come from interaction energy, so it's very difficult to calculate. And for example, we have to calculate this kind of complicated diagram using lattice QCD. And sometimes gluon create quark and antiquark pair, and these quark and antiquark annihilate and becomes gluon. This kind of process occurs everywhere. And this is effect of determinant of D, which coming from integration of the quark field. But sometimes people neglect this determinant, effect of determinant. This is called so-called quenched approximation. Sometimes people use this kind of approximation. But important thing is this hadron, this quantity, if you can calculate this quantity, we know this quantity behave like this. So sum of the exponential. And this exponential factor, each exponential factor is related to the particle mass, Mn, and momentum P from the so-called dispersion relation. And if x minus y, this separation is very large, very smallest value of E0 dominate from this quantity. Then if one can calculate this and make x minus y is large, we can extract E0. Then we can extract mass of the hadron corresponding to lowest mass corresponding to this. Of course, if you can calculate second exponential factor, you can calculate the excited state hadron mass, etc. This is a state-of-art calculation for the hadron masses. So we now consider the three different quarks, up and down and strange. So in this case, there are several hadrons. One is nucleon is proton and neutron. And in this case, we don't distinguish proton and neutron. It's almost same has mass. But we have different hadrons which contain strange quark. One strange quark, sigma, but different type lambda, and hadron which contain baryon which contain two strange quark, sigma, etc. And we have the octet baryons and decaplet baryons. And this is the most state-of-art calculation made by so-called BMW collaboration in Germany. They published this result 2008 in Science. In QCD, we have parameters, three parameters. One is coupling constant, the other is quark mass. And we have to fix this input by taking pi meson mass, k meson mass, and sigma baryon mass. So these three are input. The other 1, 2, 3, 4, 5, 6, 7, 8 are predictions. And this red symbol is QCD calculation, and this bar is experimental result, so experimental measured value. As you can see, agreement between lattice QCD calculation and experimental value is very good, as you can see from this figure. This is current status of the hadron mass calculation. So now hadron mass, I think, can be accurately calculated. So next step is hadron interaction. In this case, it's nuclear pulses. So there are some difficulties nuclear potential calculations. One is some numerical difficulty. So interaction is a kind of two-body problem. The Hadron mass is just calculate one body calculation, but interaction case we need two hadrons. This is much more difficult than one body calculation. It's more complicated diagram, and we need since we have two composite objects, we need larger volume, and we have more Monte-Carlo sampling, etc. But this difficulty can be solved by faster supercomputer. But most difficult problem is some conceptual problem. That is the definition of the potential in quantum theories. As you learn the classical mechanics, we know what is the potential. Then, if we quantize this system, we just use same potential for the quantum mechanics and calculate things. So therefore, in that sense, potential is input. However, in the case of nuclear potential, there is no classical NN potential at all. So question is, what is the potential, NN potential in QCD? This must be the output from QCD. So we have to define. That is the most difficult part of this kind of problem. So let me explain our strategy very quickly. So this is our proposal. First, we define some quantity in QCD. It's a little bit difficult, so-called we call number-based salpeter wave function, but which is defined from some QCD state and some operator. So anyway, we can define this quantity. But most important property of this quantity is as distance between two nucleons become very large, so this R becomes very large, it becomes free wave, but with some phase shift delta. So if you know the quantum mechanics and scattering problem, for large asymptotic region, partial wave behave like this, sine kr divided by kr, but with some phase shift. But important thing is this phase shift is the scattering phase in QCD. This can be shown. So this quantity has this behavior can be shown by these people. Therefore, in that sense, we think we can consider NBS wave function is a scattering wave of quantum theory, such as QCD. Since we have the scattering wave, then next step is we define non-local but energy independent potential from this equation. So since we know this, we multiply free part of the Schrödinger equation and some energy, kinetic energy of this wave, k square. And for large R, this becomes 0 because of, since it's free wave. However, it becomes non-zero at shorter distance. And this non-zero part, we parameterize phi times u, xy. This is so-called non-local potential. Then we expand this non-local potential in terms of derivative. So u, xy equal to some function of x and derivative times delta function. At the leading order, we have the no derivative term, so local function plus derivative. Then once we consider this form and plug into the previous equation here, we can easily extract potential from this equation. So if we know the wave function, NBS wave function, we multiply this operator and divide it by wave functions. That is the potential. Once we have the potential, we can calculate physical quantity, phase shift, or etc. But only the limitation is as follows. It's only considers elastic scattering. So elastic means NN go to NN. But we don't consider NN go to NN pi or NN 2 pi or etc. We don't consider such a inelastic scattering. So as I will show, this procedure gives a new method to extract phase shift or nuclear potential from QCD. We call this QCD method, and we have the collaboration named QCD collaboration. This is a member of our group containing 3 PhD students. So last maybe 10 or 15 minutes, I'll show our result, and in particular on repulsive core. So first result, we published paper 2007 together with Tetsuo Hatsuda and Noriyoshi Ishii, and using supercomputer at that time. It's called Blue Gene A at KK. Nowadays it's not so fast, but at that time it's very fast supercomputer. We used about 4,000 hours for 500 no, 2006. And we consider 2 nucleon systems. Since nucleon has spins, there are 2 different spin states. So since we have 1/2 and 1/2, it becomes total spin 1 and total spin 0. And in addition to total spin, we have the orbital angular momentum. But for simplicity, we take orbital angular momentum is 0. Therefore, we have 2 states: spin singlet state and spin triplet. This is the result of NN potential from our calculation. This is our result, but in this first calculation we use quenched approximation, so it's quenched QCD result. This is red point is our result. This blue line is the prediction of the Yukawa theory. And this is a nuclear potential I showed before. It's determined from the experiment. As you can see from these figures, qualitative future of NN potential, including repulsive core, can be reproduced from lattice QCD calculation. This is our first result. In this case, it's spin singlet potential, but similar potential has been obtained for spin triplets. So this is some responses to this result. This is a talk by Frank Grisek at Yukawa Tomonaga Symposium at 2007. So this is his statement. Just in the last few weeks, Sinya Aoki and Hatsuda reported the first calculation of the nuclear force based on QCD. They do find the hard core. Hard core means nuclear force, repulsive core. It's a major milestone in our fundamental understanding of matters. And Hiro also wrote some articles in Nature concerning this. And our paper has been selected as one of the 21 papers in Nature Research Highlights 2007, that year. And from physics, only 1, and 2 from Japan. The other one is a paper on IPS by Yamanaka, who got Nobel Prize last year. And in that article, in this highlight, they said the achievement in both computational tour de force and triumph for the theory. So the question is then, since we just calculate numerically and obtain the repulsive core, the question is, what is the origin of the repulsive core? So, since quarks are fermions, 2 quarks cannot occupy the same position. This is famous Audi principle. But quark has the color, 3 colors, and also spins, up and down spins, and also flavors, up down flavors, not spin and flavor. Therefore, in principle, 6 quarks can occupy same position. For example, proton up and proton down have this kind of configuration. So U up U down, D up, and D down, U up, U down, and red, blue, green, red, blue, green. In this case, there are no pairs which have same quantum number. So this is possible. However, but allowed color combinations. For example, if you change this color to red is not allowed, because this, if you make this red, which contradicts with this, because of power principle, it's not allowed. So in that sense, in this case, some cases allowed, but some does not allow, are not allowed. So plus some interaction of the quarks makes repulsive core. That might be one possibility. But if this kind of interpretation is true, what happens if we consider the more quarks, more flavors, strange quark? What happens if strange quark are added? In this case, if you have U and D and S, then we have lambda and lambda interaction can be considered. UDS, UDS. In this case, since we have UDS, UDS, if the spin are up and down, and in this case down and up, this case is up and down. In this case, all spin and flavor are different. All color combination is allowed. For example, this case is U and U have same colors, it's allowed also. Of course, you can have different colors, but all color combinations are allowed. If the previous interpretation is correct, in these cases, repulsive core may disappear. Actually, we calculated omega-omega interaction and found indeed there is no repulsive core. So instead, we have the attractive potential, attractive core, not repulsive core. So attraction is very strong. So this calculation suggests Pauli principle is important for the understanding of the repulsive core. And byproduct, since this force is attractive at all distance, one may expect that there might be a bound state for this channel. Actually, people predicted bound state of this channel, so-called H divarium. This is a possible six quark state, UU, DD, SS, predicted by model calculation, but not observed experimentally yet. And using this potential, and we calculate the Schrödinger equation, and found one bound state indeed exists. And our calculation is still contains some limitation, like pion mass is much heavier than experimental value, and etc. But by changing the pion mass in our calculation, we always observe the bound state in this calculation between binding energy from 25 to 50 MeV. So in case of NN, we have this bound state called deuteron, which have this kind of wave function because potential has this kind of shape. But for the H divarium case, its potential is all attractive, no repulsive core, and the wave function is concentrated or at a short distance. It's more compact than deuteron binding bound state, like this. So let me conclude. The potential method, or we call the Hall-QCD method, is a new but very useful to investigate not only the nuclear force, but also general baryonic interaction, like including omega-omega, numerically. So this description gives some understanding, not complete, but some understanding for repulsive core. So method can be easily applied also to meson baryon or meson-meson interaction. And some postdoc and students working on these new areas. And our general strategy is following. So we calculate potential. A general strategy to nuclear physics from QCD is the following. We calculate some interaction, two-body interaction from Lux QCD like this. So we get potential. And using this potential, we consider now Schrödinger equation with many body problem. Then we can calculate nuclear physics with this potential. And from this calculation, we can investigate property of the neutron star or supernova. So there are some remarks, but maybe I leave the time to your question. Thank you.
Questions?
You mentioned that this is another way of calculating phase shifts.
Yeah.
Have you tried to calculate phase shifts compared to, like, Boucher's method or so on?
Yes. Not Richard method, but I have some figures, but not included in this. But for example, if we calculate potential like this, and fit this potential, this blue line, and solve the Schrödinger equation, and we get phase shift shape like this.
Right, but that was not my question. I was wondering if you can get, suppose to calculate this and can get the phase shift that you calculate will be match up with the usual way of calculating the phase shifts at different, say, lattice,
Okay,
volume dependence or momentum dependence.
I'll talk about tomorrow, but then maybe show some. This is pi case using same technique and calculate phase shift. This is our result. This is blue point is the result from Lucian. So agreement is very good for very small mass, but for higher energy, Lucian method is very large error, but our method is error is small and consistent with their result.
Any other questions?
Maybe I ask directly. Why can people use the approximation method at lattice QCD? Why can people use it to do this approximation? Why this method will work?
This question is asked why lattice QCD works.
Yeah, partly due to the good superconductor. But lattice QCD contains many gluon interaction automatically because of this U. So usually people in perturbation theory people use A, but instead of A we use U, which contains infinite number of A in some sense. So in that sense we can calculate non-perturbative quantity in that case. That is very different from usual perturbation theory. The main reason is, as I said, this is well-defined statistical system. So in that sense, we don't use any approximation in this calculation. Of course, approximation is space-time we approximate, but in the mass integral calculation, we don't use any approximation. People usually use approximation like perturbation theory calculating quantity, but that is very difference between lattice and usual continuum calculation. That is good.
Any other questions? Yeah, that's his question. He wants you to finish the remark.
One important remark is potential itself is not physical observer. So, I mean, experimentally we cannot determine potential. That is very important thing. So, potential in some sense is sort of scheme-dependent quantity. For example, if choice of how we define the nuclear field is potential depend on your choice. It's a very good analogy is running coupling constant and QCD. Running coupling QCD is scheme dependent. It's not physical observer. Physical observer is scattering up. But the good point is the running coupling and potential, although it's not physical observer, if once we know the potential, we can calculate physical observer like scattering up. And also physics becomes very clear. For example, if we have the potential, we say interaction becomes very repulsive at short distance and attractive for long distance. Of course, it's not physical, it's some scheme-dependent statement. But also it's true for running coupling. We say asymptotic freedom in running coupling. But of course, this asymptotic freedom is scheme-dependent statement. But we know its use. This is so one very one remark.
Any other question?
I'm sorry. You say that the lambda particle don't have the repulsive core. Then I wonder what will happen when they come together.
Yeah, so that is H divided principle. So if lambda is attraction is strong, so they could form bound state. So for H divided. But of course, our calculation is some ideal situation. So in reality, situation becomes more complicated. And we are now trying to understand what happens this H baryon in nature. And our conclusion is we have some kind of so-called resonance, not bound state, but some resonance for this channel. And we hope this resonance will be measured in observing experiment, J-Park experiment in the future.
So how does the spin structure change the hot core picture? Spin structure.
Spin structure. For spin singlet case, leading potential is only one potential. But spin triplet case, we have two structures. One is so-called central potential, but the other is so-called tensor potential. And we can also calculate tensor potential. And so this blue is spin singlet potential, central potential, and green is spin triplet central potential, and red is tensor force. So I think in nature, because of this tensor force, neutron bound, but not dineutron bound. So in that sense, spin dependence is very important, and which distinguishes the neutron bound scale, but not dineutron or dipole bound. So, but again, our calculation is contains some approximation, still not show the neutron binding, but